Okay, good morning. So we're going to the second lectures for today. The major factors affecting the performance and emissions of a IC engine. Okay, so here list some of the factors. Actually, yeah, a lot more factors are not included in this lectures. Here, I just highlight some of the major factors. Okay, so first one is a few properties. And second one, this one actually we just from the previous lectures actually we can understand already, correct? Second one is a ball geometry. Okay, this one can affect the airflow, affects the turbulence, and thereby affects the combustion process and the emission formation. The next one is the ignition timing. Okay, ignition timing. This one can also affect the efficiency of the engines and also affects the major emissions. The next one is a fuel injection strategy. Right, we have different fuel injection strategy and to optimize the performance and minimize the major emissions. And we have direct gasoline injection. Now this technology is more and more commonly used in gasoline engines to improve the efficiency. So next one is a variable compression ratio, which means based on the engine is operating at different loads or different conditions, then we can change the compression ratio so that we can achieve some more optimal performance at all kinds of engine speed, all kinds of engine load conditions. So next one is a charger or supercharger. This one is commonly used for both gasoline engines and diesel engines to improve the power density and increase the efficiency, correct? Okay, so last one is so-called ignition methods. We use different ignition methods also can improve the combustion process. Of course, also we have some different design, for example, HCCI engines, RCCI engines, and so on. Okay, so first one I want to share with you guys is the ball geometry on the performance and emissions of these engines. Here we show you three different designs. The first one is Omega combustion chamber. Okay, Omega combustion chamber. The second one is a hemispherical combustion chamber or HCC. The last one is a shallow depth combustion chamber or SCC. So we have down suspension in the four-stroke engines. Okay, this four-stroke engines is both sides is 9.2 cm, and the stroke is 9.38 cm, and the swept volume or displacement is 2.5 liters, and the compression ratio is 80.5, and here we have turbocharger, and the original design of the piston ball geometry is omega shape. And the rated power is 75 kilowatts at 3,600 RPM conditions. And the fuel supply system is a diesel Tamara fuel supply system. And the fuel injectors has a 6 injection hole for each injector. Okay, so firstly, we have simulated the flow fields in the three different ball geometries, okay? And this is omega, HCC, and SCC, correct? At different engine speed conditions. So firstly, compare this one and this one, we can see with the increase of engine speed, a stronger turbulence will be formed, correct? Similar to the other two ball geometries, correct? HCC and SCC, correct? Okay, if we compare these three different ball geometries, so this one, the omega and HCC and SCC. So if compare these three different designs, we can easily understand. Okay, OCC produce the strongest turbulence. Okay, strongest turbulence, correct? Followed by this one, HCC, and SCC produces the least stronger, least strong turbulence. Okay, then we compare the power produced by these three different ball geometry design and also the major emissions produced by these three different designs. So here compares the indicated power. This one also you can easily convert into indicated thermal efficiency, correct? So at lower engine speed conditions, actually you can see the power produced by these three different designs are quite similar, and the SCC produces slightly higher power, and at medium speed conditions, okay, so you can see the Omega design produce more power. At higher engine speed conditions, also the Omega design produce most power, right? So it combines these three different designs because OCC produces strongest turbulence, and this strongest turbulence can promote the combustion process, okay? Thereby increase the power produced by the engine, correct? Okay, interestingly is that if we compare the SCC and compare the HCC and SCC at lower engine speed conditions, actually you can see SCC even produce more power, compared to HCC and OCC. Why? So why at lower engine speed conditions, actually SCC produce more power? Okay, because this kind of design, actually the fuel, okay, the spread fuel can be easily spread to other position. Okay, the fuel can be easily spread to other position from here. Okay, at lower engine speed conditions, because at lower engine speed conditions, turbulence is not so important because at lower engine speed, which means that the time for combustion process is not enough, correct? So under these conditions, the turbulence is not so important anymore. Instead, because this kind of design, the fuel can be easily spread to other position, thereby can improve the combustion process. That's why for the marine engines, actually you can see for all the big marine engines, actually the piston top is a flat. Okay, it's a flat design. Correct? Do you know for the big engines, the marine engines, usually the piston top actually is a flat. Okay, they don't design any ball geometry or other geometry. They just use a flat piston. Okay, because for low speed engines, the time for combustion process is sufficient. Okay, so the best way actually is to facilitate the spread of fuel to everywhere, correct? However, at higher engine speed, for example, 3,600 RPM, because the time for combustion process is only 1/3 of the engine speed, correct? Which means that the combustion process should be very fast. Otherwise, the fuel cannot be fully burnt. That's why at higher engine speed conditions, we can see Omega design produce the highest power because this kind of a design produce the strongest turbulence. Okay, produce the strongest turbulence. Okay, so the next one is the CO emissions and the NO emissions. So basically, we can see the CO emissions. SCC produces the highest CO emissions, and followed by the called the HCC, and the OCC produces the smallest one, correct? High engine speed conditions. Again, because the turbulence is different. OCC has the strongest turbulence. Okay, so we can see the CO emissions will be smallest, right? The CO emissions will be smallest because the strong turbulence can improve the combustion process. Okay, so most of CO will be oxidized. Okay, on the contrary, NO emissions okay, actually is the highest for OCC because again, because the strongest turbulence, the combustion process is the best. As a result, okay, the NOx emission will be produced more because as we know, the NOx emissions is a product of a high combustion temperature. So the better combustion process, the higher the temperature and the higher the NOx emissions. Okay, the higher the NOx emissions. Okay, the next one I want to introduce is ignition timing on the performance and emissions of gasoline engines. Okay, so firstly, that comprises three different fuel injection timing, ignition timing. Okay, so first one, the ignition timing is occurs at TDC or top dead center. The second one, the spark timing is minus 35 degrees CA. Okay, it is 35 degrees CA before TDC. And this one is 70 degrees before TDC. So if comprises three different ignition timing, so can see actually this one produces the highest efficiency. It is about 26.2%. And this one, okay, it's the lowest. Okay, the efficiency is only 23.9%, and this one 24.1%. Okay, so why as we advance ignition timing, the efficiency drops so much? Anyone knows? As we advance the ignition timing, okay, to 35 degrees CA before TDC, so can see the efficiency drop a lot, correct? If comparison, and this is the optimal one. So can see the efficiency drop a lot, correct? So why like this? Anyone else?
Complete burning of fuels.
Mm-hmm.
In the
Okay.
last case, the complete fuel is burned.
Mm-hmm. Okay. Okay, good. Yeah, because in this case, if spark timing is too earlier, as we know, a lot of fuel will be burned before TDC, correct? Okay. And the pressure in the cylinder will increase during the compression stroke. Okay, as we know, in compression stroke, the work done is negative. So work done is negative, correct? So the greater work done in the compression stroke, the lesser the efficiency, correct? Because compression stroke, the work done is negative. It is not positive, it's negative, correct? So we should minimize the work done in the compression stroke. Okay, so next one, as we retard the ignition timing, okay, for example, spark timing at TDC, then we can see the efficiency also drop a lot compared with this optimal one. Why? Okay, this one actually is also very simple because if your injection ignition timing is too late, most of the combustion process occurs in the expansion stroke, correct? So some of the energy actually didn't function for the whole expansion stroke. Okay, some of the fuel actually is not produce work for the whole power stroke, correct? Because some of the fuel only burn at very late, correct? So work done will drop, correct? And the efficiency will decrease. So here we show you, okay, the ignition timing is very important for the engine to achieve the highest efficiency. Okay, the next one I want to introduce is locking and its impact on the gasoline engines. Here we show you the in-cylinder pressure versus the time, okay, or crank angle, okay. So you can see this one is a normal combustion process, and this one is an abnormal combustion process with a detonation. Okay, so we can see with detonation, the pressure in the cylinder will fluctuate. Okay, will fluctuate. Okay, And this fluctuation will produce a lot of noise and can seriously can destroy the piston, destroys the engine. So here we show you a picture. Okay, this picture actually show you this piston is destroyed under this detonation combustion process. Okay, detonation combustion process. So now let me show you a video how this kind of locking or detonation combustion occurs. So let me show you a video. So did you see the difference between the normal combustion process and the locking combustion process? Here, okay, so I'm actually show you the locking occurs, correct? In the earlier stage here, okay, so this one is a normal combustion process. Okay, regular combustion process or normal combustion process, correct? So for normal combustion process, we can see the flame will be transported from the spark plug to the rest, okay, to the cylinder wall, correct? So this okay, flame will transport from the spark plug to the cylinder wall, okay? So will transport from this position to the rest of the engine, to the rest of the cylinder, correct? However, in the however, in this locking a combustion process, we can see firstly we have this flame will transport from the spot to other place at the same time. Do you notice this position? Actually, auto ignition occurs. Okay, so auto ignition occurs in this position, in this far away position from the spark plug, right? Thereby we can see the combustion process in this area will produce a wave, pressure wave. And at the same time, the auto ignition flame produced in this position also produce a pressure wave. So when these two pressure wave impact each other, then will produce a so-called pressure wave, so-called the rapid increase of pressure. Okay, rapid pressure of increase of pressure. Okay, thereby produce locking. So we can see this is a pressure wave will impact each other, right? Thereby produce a big vibration on the pressure. Okay, so that's why you can see from here, from this the in-cylinder pressure versus triangle curve. So you can see the pressure in the cylinder will fluctuate, and the peak pressure also is much higher than this one. Okay, than normal combustion process, correct? Because this this is locking. Okay, so here actually we show you what is the closest forces knocking to occur. This one actually can see the in the exhaust valve we have carbon deposition, correct? Okay, so carbon deposition, if too much carbon deposition, will not only affect the exhaust gas flow, and also okay part of the carbon deposition will drop. Okay, during the operation process. Okay, some of the particles will drop, and because this soot particles has high temperature, can ignite the fuel admixture. Okay, so let me continue. Okay, so in this part, actually we show you how the pre-ignition occurs in the engines. Okay, this pre-ignition also is not favorable for the engine, correct? Because by this pre-ignition, which means we advance the ignition timing, just like we have introduced, okay? If the ignition timing is too earlier, then the efficiency will drop, okay? So this one is caused by the imperfect contact between the spark plug and the supporting structures here, correct? You can see, okay, so we have the gap here between the spark plug and the supporting structure. We have gap. This one will affect the heat transfer. Okay, thereby the spark plug become too hot, and then will auto ignite the fuel admixture. Okay, before the optimum timing. Correct? So you can see actually here, you can see the piston has been destroyed, because this is a detonation, okay, detonation. Okay, so yeah, it's important for the gas engines to avoid cases kind of knocking occur. Okay, so next one I want to introduce is a fuel injection strategy on the performance and emissions of these engines. Here we show you the fuel injection pressure on the soot luminosity, okay, luminosity and the flame size at the end of the injection. So here we show you the soot luminosity and the flame size. Okay, these are two rows of pictures actually at different net wavelengths. Okay, this one is the net wavelength is equal to 650 nanometers, and this one is 800 nanometers. Okay, so the picture more or less quite similar because we only change the net wavelengths. Then the signals produced by these two different net wavelengths actually should be similar, correct? Okay, should be similar. Then we compare this one and this one. So you can see the fuel injection hole is the same, 0.16 millimeter, 0.16 millimeter, but fuel injection pressure is different. Okay, this one, fuel injection pressure is 100 megapascal. This one 200 megapascal. So you can see with the fuel injection pressure, the flame size will increase, correct? The flame size will increase. However, the intensity will drop. The intensity will drop, correct? And as we further increase to 300 megapascal, okay, between this one and this one, comprises two. Actually, they are quite similar. They are quite similar, correct? And okay, this one is when as we decrease the fuel injection hole to 0.08 mm, and the fuel injection pressure is still 100 megapascal. So it compares this one, the first one, and the last one. So you can see the size will decrease. Okay, the size will decrease because the fuel injection amount will decrease. Fuel injection amount will decrease, correct? Because the whole injection hole size decrease, which means much lesser fuel will be injected. So the soot particles luminosity will drop, will decrease, both in terms of size and the intensity, correct? Okay, so here shows the distribution. So again, this one is suppose 100 megapascal, and this one is 200 megapascal, and this one is 300 megapascal. Okay, so we can see with the fuel injection pressure. So we can see the integrated luminosity will decrease. Okay, will decrease. Okay, this one is easier to understand because with the increase of the fuel injection pressure, okay, the fuel droplets will become smaller and smaller. Correct? And this small droplets can improve the combustion process. Can improve the combustion process. As a result, the soot particles produced by the combustion process will decrease. Okay, because higher fuel injection pressure, okay, the fuel droplets will become smaller, and the combustion process will be improved. Okay, thereby the soot particles produced will decrease. Okay. Okay, the next one I want to introduce is multiple injection, commonly used in engines to improve the efficiency and reduce the noise and also reduce the NOx emissions. Okay, reduce the NOx emissions and HC emissions and the CO emissions. Okay, usually okay, this is a pre-injection. Okay, so before this one is the main injection. Before the main injections, we can employ the pre-injections, okay, to form a small amount of fuel mixture. Okay, so by this design, actually we can produce a more smooth combustion process and reduce the peak pressure increase. Okay, reduce the peak pressure increase rate. So by this design, we can control the noise produced by the engine. And usually the NOx emissions are formed in this duration, okay? Because this duration is a lot of a premix combustion process will occur. So the temperature has the highest value, and under conditions, a lot NOx emissions will be produced, okay? Then the pause, okay, this one is a pause injection. After the main injection, we have pause injection. Okay, this pause injection is designed to increase the exhaust gas temperature. So by increasing the exhaust gas temperature, actually can reduce the CO and HC emissions. Okay, we can reduce CO and HC emissions because by pause injection, we can increase exhaust gas temperature. Higher temperatures are favorable for the CO and HC emissions, correct? So let me show you another video on the multiple injections, okay? Okay, so in this video, actually we can see multiple injections are commonly used for these engines to adjust the scores amount to minimize the noise and also to minimize the major emissions like CO and HC emissions. So in this case, actually we show you the injection. Actually there are four injections, correct? So let me go. Okay, so here we can see actually in this engine, we have four injections. We have two pre-injections, one main injection, and one post-injection, correct? Okay, so the pre-injection, here he mentioned, okay, can rank the combustion process. Okay, so that the combustion process, the flame increase or the temperature increase not too fast. Okay, if the pressure increase, the temperature increase too fast, then what happen? Then will produce noise. Okay, the engine tends to produce noise, and the engine will start to shake or vibrate. Okay, so by using pre-injection, we can reduce the because pressurized rate. And by the post-injection is to raise the exhaust gas temperature, so that we can reduce the CO, HC emissions, and also can use for the regeneration of the particle subparticle filters. Okay, so now we better understand, okay, the effect of fuel injection pressure and the fuel injection strategy, multiple injections, is impact on the performance and on the major emissions, correct? Okay, the next one I want to share with you guys is gasoline direct injection engines. Unlike conventional gas engines, the air fuel mixture are formed directly in the combustion chamber of the engines. Okay, in the gasoline direct injection, in the traditional gas engines, we know the gasoline fuel is injected into the intake manifold and then premixed with the air, then supplied to the engine, correct? But in gasoline direct injection engines, actually the fuel is injected into the combustion chamber directly. Okay, so here we show you the gasoline direct injection, correct? Only pure fresh air will enter the intake valve, okay, enter the engines through the intake valve, correct? Okay, and the fuel injection pressure also is much higher than traditional gas engines. Okay, for example, the fuel injection pressure is about 200 bar. But in the conventional gas engines, the fuel injection pressure is only a few bar. Okay, 3 bar or 4 bar. Yeah, something like that. Okay, so again, let me show you another video to show you how the direct gasoline injection engines works. Okay, so in this video, actually, I will show you how the GDI engine works. This GDI engine actually is the fuel injection is through the high pressure fuel injectors, correct? So it's quite similar to the diesel engines, correct? So by this way, by this design, actually the compression ratio of the engines can be increased. Okay, the compression ratio of the engine can be increased, correct? Thereby, we can increase the efficiency of the engines. Meanwhile, actually by this kind of design, the fuel air ratio can be more precisely controlled. The fuel air ratio can be more precisely controlled. Thereby, we can further optimize the performance of the engine. Okay, so here we show you the major advantage of GDI engines. We can increase the efficiency by 50%, increase efficiency by 50%, and increase power outputs. Okay, increase power outputs because just like I mentioned, by using GDI engines, we can realize higher compression ratio. Okay, thereby increase the output power and the efficiency. And some engines operate a full air intake, which means that the throttle valve is fully open, and then the engine load is controlled by the fuel injection amount. Okay. So by this design, the airflow resistance will be minimized. Air resistance, okay, airflow resistance will be minimized. Okay, thereby we can optimize, okay, maximize the volumetric air supply, correct? Thereby improve the efficiency and maximize the power produced by the engine. Okay, the emissions can also be more accurate control with the GDI system because we can more precisely control the fuel injection amount and control the fuel air ratio. Okay, so however, GDI engines also has some disadvantage. For example, it is much more expensive than the traditional gasoline engines. Okay, because we import high pressure fuel injection system, correct? And increase the complexity. And the second major shortcoming is increased carbon build-up occurs in the backside of the intake valves that over time will reduce the airflow to the cylinders. Okay, to the cylinders. Therefore, reduce the power. Okay, this one's due to the fact because GDI, okay, there's no port injection, correct? Also, gasoline fuel will be directly injected into the combustion chamber, so the fuel don't flow through the intake valve, correct? As we know, actually, the diesel fuel usually contains detergent, okay, detergent. This one can help clean the intake valve, okay? So if there any carbon deposition on the intake valve, then because the fuel contains detergents, can help to remove or clean the intake valves. However, in GDI engines, because the fuel don't flow through the intake valve, so cannot help clean the carbon deposition. Okay, so with time, more and more carbons will deposit on the back surface of the intake valve, thereby reduce the airflow. Correct? Okay, so next one, I want to introduce a variable compression engines. Okay, as we know, the higher compression ratio means a higher efficiency, means a higher power output, correct? So for engines, for gasoline engines, actually we can adjust the compression ratio when the engine is operating at different conditions. For example, when the engine is operating at partial load conditions, we know under the conditions, okay, the fuel air ratio will be low. Okay, fuel air ratio will be low, will be linear, correct? So under the conditions, actually we can increase compression ratio. to improve the efficiency, correct? Increase the power. However, when the engine is operating at higher or full load conditions, then under the conditions, we can reduce the compression ratio. Okay, can reduce compression ratio when the engine is operating at higher engine load or full load conditions. Then we can reduce compression ratio. So by this way, we can reduce the locking tendency and reduce the peak pressure. Reduce the peak pressure. Okay, so by this design, we can make sure the engine is always operating at the maximum, sorry, not maximum, okay, operating at the optimal conditions, okay? So here we show you the how to control change the compression ratio. So we can see we can adjust the heads of the crankshaft, okay, thereby adjust the compression ratio, correct? By adjusting the heads of the crankshaft, we can control the compression ratio. As we increase the head of the crankshaft, then the compression ratio will be increased. As we drop down the crankshaft, then the compression ratio also will be decreased. Correct? So at full load conditions, okay, we can reduce the compression ratio. At partial load conditions, we can increase the compression ratio. So by this design, we can make sure the engine is always operating at optimal conditions. Okay. Okay, so last one I want to introduce is a turbocharger or supercharger. Okay, this one is very useful for the engine to achieve higher power density and also increase overall efficiency. Okay, so let me show you another video. Okay, so here we show you the exhaust manifold. It is combined with the turbine. Okay, this one is a turbine and this one is a compressor. So this engine is a four-cylinder engine, correct? Okay, now we can see the exhaust gas will be discharged from cylinder by cylinder. Then the exhaust gas will be used to drive the turbine, correct? And then this turbine is connected with the air compressor, okay, with air compressor. So the fresh air will be compressed to increase the pressure, increase the temperature. Okay, so by this way, okay, this one is a turbocharger, okay, turbocharger. So by this way, we can supply the more fresh air into the engine, and thereby the engine is able to produce more power, correct? And also can increase the efficiency by this design. Okay, so here we'll show you how this turbocharger works. Okay, so turbocharger can significantly increase power density and also increase the efficiency. Okay, also increases the efficiency. In addition, it is able to reduce the major emissions like HC and CO emissions. So why the turbocharger can reduce major emissions like CO and HC emissions? Anyone knows? Why increase the pressure? We can reduce the HC and the CO emissions.
Better combustion of the
Yeah,
particles.
yes, better combustion process because the higher pressure, correct? Higher pressure, higher temperature can enhance the oxidation of HC and the CO, correct? thereby can improve the combustion process and reduce the major emissions like CO and HC emissions. However, NOx NOx emission will increase. Okay, the NOx emission will increase. Correct? Okay, so it's time. We still have one more slide. This one can introduce maybe next class, next the tutorial class. Okay, so we'll stop here. We'll have break about 10 minutes. Then we can come back.